Welcome! In this session, we'll explore LeetCode problem number 1948, delete duplicate folders in system. This is an interesting and challenging problem that involves identifying and removing duplicate folders within a file system based on their structure. Let's dive in and understand the problem, its nuances, and how to effectively solve it. In this problem, you are tasked with cleaning up a file system by removing duplicate folders. Each folder is represented by a path, which consists of a list of directory names. Two folders are considered duplicates if they have the exact same structure and content, meaning that both the folder and all of its subfolders are identical. When a duplicate is identified, both the original folder and its duplicate must be removed entirely. Once all duplicates have been removed, the remaining file system needs to be returned as a list of paths, sorted in lexicographical order. The input consists of a list of paths, where each path is a sequence of strings representing directory names from the root to a specific folder. The output will also be a list of paths, formatted similarly, but without any duplicates. Let's dive into some examples to illustrate how this works. Here's the first example. The input consists of several paths, A, C, and D, along with their subfolders. For instance, A contains subfolders X and Y, and similarly, C contains X and Y as well. The output for this example is a simplified list containing only the directory D and its subfolder Z. This is because A and C are duplicates, they both have identical structures and contents, including their subfolders. Since duplicates must be removed entirely, both A and C are deleted, leaving only D and Z in the final result. This shows how the problem focuses on recursively identifying and removing duplicate structures. To better understand the reasoning, let's break down the explanation for this example. The directory structures rooted at A and C are identical because they both contain subfolders X and Y, and these subfolders themselves are identical in both cases. Since the directories A and C are duplicates, they are removed entirely from the file system. The only directory left is D, along with its subfolder Z, because it does not have a duplicate. This highlights the recursive nature of the problem. Subfolders are compared first, and if they match, the parent folders are considered duplicates as well. In the second example, the input paths represent two main directories, A and C, each containing a subfolder B, which further contains the subfolders X and Y. Here, both A and C have the exact same structure, including the subfolder B and its contents. Since the directory structures rooted at A and C are identical, they are both considered duplicates and removed. As a result, the output is an empty list, because no directories remain in the file system. This example emphasizes that when entire structures are duplicates, the result may be completely empty. In the third example, the input paths describe two main directories, A and X, each containing a subfolder B, which itself contains subfolders C and D. The directory structures rooted at A and X are identical because both contain the same subfolder B, and B has the same subfolders C and D. Since these structures are duplicates, both A and X are deleted entirely, along with all their subfolders. The output is again an empty list because no directories remain in the file system. This example reinforces the idea that duplicates are identified recursively, and any folder with identical subfolders will be treated as a duplicate and removed. Now for the constraints and edge cases. The problem constraints ensure that the input is manageable within the given limits. There can be up to 10,000 paths, and the total length of all paths combined is at most 100,000. Each directory name is a lowercase English letter string with a maximum length of 10, and all input paths are guaranteed to be unique. For edge cases, if the input is empty, the output will also be an empty list. If no duplicates exist, the output will be the same as the input, but sorted lexicographically. The solution must also efficiently handle deeply nested paths, where many levels of subfolders are involved. Finally, if every folder in the system has a duplicate, the output will be empty, and if there's only a single folder, it cannot have a duplicate, so the output will simply match the input. To solve the problem of deleting duplicate folders in a system, we first need to clearly define what constitutes a duplicate. In this case, duplicate folders are those that share the exact same structure and content, including all their subfolders. One approach we could consider is a brute force method. Here, we would compare each folder's structure and content against every other folder. By using recursion or constructing a tree to represent the directory paths, we would traverse the file system and perform pairwise comparisons of subtrees. While this method is intuitive since it directly examines the problem, its time complexity is quadratic or worse, making it unsuitable for larger datasets. For example, if the system contains tens of thousands of folders, the comparisons quickly become computationally prohibitive. Additionally, the space requirement to store the tree structure only adds to the inefficiencies. Recognizing these limitations, we need a more scalable strategy. This leads us to consider an optimized approach based on hashing and post-order traversal. Using hashing with post-order traversal, we can significantly improve efficiency by avoiding redundant comparisons. The intuition here is that any subtree can be uniquely serialized into a string that captures its structure and content. By hashing these serialized strings, we can efficiently determine the frequency of each subtree. The process unfolds in a few key steps. First, we represent the directory structure as a tree. Then, we use post-order traversal to serialize each subtree into a unique string representation. A hash map is employed to count how many times each serialized subtree appears. Finally, we perform another traversal to identify and delete folders with duplicate serialized subtrees. This approach is efficient, as each node in the tree is visited only twice, keeping the time complexity linear relative to the number of nodes. Similarly, the space complexity is linear, as we only need memory for the tree and the hash map. Not only is this method scalable for large inputs, but it also strikes a balance between simplicity and performance. While other methods, such as using graph isomorphism or preprocessing, were considered, they proved to be less practical due to their added complexity. Ultimately, we chose the hashing with post-order traversal approach for its efficiency, scalability, and clarity. Several key observations support this decision. First, the process of serialization allows us to represent subtrees with identical structures and content as the same string, making hashing a natural and effective choice. Second, post-order traversal is particularly well suited for this task because it processes child nodes before their parents, enabling us to identify and handle duplicate subtrees from the bottom up. With a time complexity of O(n) and space complexity of O(n), this approach is well suited for handling the large-scale inputs typical in this problem. However, it's important to acknowledge trade-offs. While brute force is conceptually simpler, it's computationally prohibitive for larger datasets. Alternative graph-based methods or pre-processing steps, on the other hand, introduce unnecessary complexity without offering significant performance benefits. By leveraging hashing and post-order traversal, we ensure a solution that is both practical and performant, making it the optimal choice for addressing this problem effectively. To solve the problem of deleting duplicate folders in a system, we start by structuring the input into a tree format. This is essential because folder hierarchies naturally resemble trees, where each folder can have subfolders, and so on. The first step is to create a root node representing the entire file system. As we traverse the input paths, we sequentially add folders as child nodes under their respective parents. To make this efficient, we can use a hash map to store the children of each node for quick access. Once we have a tree, the next step is to prepare for identifying duplicate folders by serializing the structure of each subtree. This involves performing a post-order traversal, where we process child nodes before their parents. For each node, we generate a string that uniquely represents the subtree rooted there. For example, a folder might be serialized as folder, subfolder 1, subfolder 2, capturing its contents in a recursive fashion. These serialized subtree representations are then stored in a hash map, where the keys are the serialized strings and the values are the nodes that share that structure. This allows us to efficiently detect duplicate subtrees. To identify duplicates, we traverse the hash map and look for serialized strings that appear more than once. Nodes corresponding to such strings are marked as duplicates. After identifying duplicates, we proceed to delete them from the tree. This involves traversing the tree again and removing all nodes flagged as duplicates. It's important to update the parent nodes to ensure that the deleted folders are no longer part of the tree structure. Finally, we need to reconstruct the output. This requires a pre-order traversal of the updated tree to generate the paths for each remaining folder. These paths are then stored in a list, which represents the resulting folder structure after duplicates are removed. Several key insights and data structures make this algorithm effective. First, post-order traversal is crucial because it ensures that child nodes are processed before their parents, which is necessary for accurate subtree serialization. Using a hash map to store serialized strings allows us to achieve constant average time complexity for lookups and insertions, making the process efficient. The hierarchical tree structure aligns perfectly with the problem's folder organization, making it natural to use. It's also important to consider potential edge cases, such as when all folders are unique or when nested duplicates appear at different levels of the tree. The main data structures involved are the tree itself, where nodes represent folders and subfolders, a hash map for storing and checking serialized subtree structures, and a set to track nodes marked as duplicates. The algorithm's time complexity is linear, as each step, tree construction, serialization, duplicate detection, and reconstruction operates in O(n) time, where n is the total number of folders. This ensures scalability for large inputs. In terms of space complexity, the algorithm is also linear, requiring O(n) space for the tree storage and the hash map. Let's now explore an example to clarify these steps. Consider an input where we have folders A and B, each containing subfolders X and Y. First, we construct the tree, creating a root node with children A and B, and further adding X and Y as subfolders under both. Next, we serialize the tree using post-order traversal. This means we process the leaf nodes first, resulting in the serialized strings X, Y, and XY for both A and B. These serialized strings are stored in a hash map, allowing us to detect duplicates efficiently. Upon examining the hash map, we find that the serialization XY occurs twice, indicating that the subtrees rooted at A and B are duplicates. To address this, we delete these subtrees from the tree. Once the duplicate folders are removed, the tree is effectively empty, as all folders in the input were duplicates. Finally, we reconstruct the output by performing a pre-order traversal of the updated tree. Since the tree is empty, the resulting output is an empty list. This demonstrates how the algorithm successfully identifies and removes duplicate folders, leaving only unique folder structures in the output. Here we begin by importing the necessary modules and defining the delete duplicate folder function within the solution class. The first step is to build the folder structure as a tree. We start with an empty dictionary called root, which will serve as the root of our tree. For each path in the input paths, we traverse through the folders in that path. If a folder doesn't already exist in the current node, we initialize it as an empty dictionary. This ensures that the tree structure is dynamically created as we iterate through all the folder paths. Once the tree structure is built, we move to the next step, serializing subtrees. Here, we define a helper function, serialize, which recursively traverses the tree and generates a unique serialized string representation for each subtree. If a node is empty, it returns an empty string. Otherwise, it concatenates the folder names and their serialized children in sorted order, delimited by parentheses. These serialized strings are stored in a default dict called subtree_map, where the key is the serialized string, and the value is a list of nodes that correspond to that subtree. This map allows us to group and identify duplicate subtrees efficiently. Now, using the subtree_map, we iterate through its values, which are lists of nodes that share the same serialized structure. If a serialized structure appears more than once, meaning there are duplicates, we clear the duplicate subtrees by calling the clear method on each node in the list. This effectively removes the duplicate folder structures from the tree. After removing duplicates, the next step is to reconstruct the remaining folder paths from the clean tree. To accomplish this, we define another helper function, collect_paths, which recursively traverses the tree. For each folder in the current node, the function appends the folder path to the result list and continues the traversal with the updated path. This ensures that all valid, non-duplicate paths are collected. Finally, the function returns the result list, which contains the clean folder paths. This completes the process of deleting duplicate folders and generating the desired output. Here, we start by defining the delete duplicate folder method, which takes a list of folder paths as input. The first step is to construct a tree representation of the folder structure. We create a root node using a custom node class. For each folder path in the input, we iterate through its components and build the tree by adding child nodes as necessary. This ensures that all folder paths are represented in a hierarchical tree structure. Next, we move on to serializing the subtrees. We use a helper method called serialize, which traverses the tree and generates a unique string representation for each subtree. These serialized strings are stored in a map called subtree map, where the key is the serialized string, and the value is a list of nodes with the same structure. This allows us to identify duplicate subtrees efficiently. Once we have the serialized data, we iterate through the map, and if a serialized subtree has more than one node associated with it, we clear the children of all those nodes. This effectively removes all duplicate subtrees from the tree structure. After removing the duplicate subtrees, the final step is to regenerate the folder paths from the clean tree structure. To achieve this, we define a helper method called collectPaths. In the delete duplicate folder method, we call collectPaths with the root node, an empty list to represent the current path, and a list to store the resulting paths. The method traverses the tree recursively, adding folder names to the current path and saving copies of valid paths to the result list. Within the node class, we define a children map to store the child nodes, which allows us to maintain the hierarchical structure. The serialize method, used earlier to identify duplicates, recursively generates a string representation of each subtree. It ensures a consistent order by sorting the child nodes alphabetically, so the serialization is deterministic. Each serialized subtree is added to the subtree map, and any duplicate subtrees are identified and cleared. This combination of tree traversal and serialization ensures that all duplicate folders are effectively removed. The collectPaths method is designed to rebuild the list of folder paths from the clean tree. It uses a depth-first traversal approach, iterating through each node's children. For every child, the folder name is added to the current path, and the path is added to the result list as a new entry. The method then recursively processes the child node, exploring deeper levels of the folder structure. Once all children of a node have been processed, the folder name is removed from the path to backtrack and continue exploring other branches. This ensures that all valid folder paths are collected in the result list in the correct order. By combining this method with the previous steps of building the tree, serializing subtrees, and removing duplicates, the program successfully generates a list of unique folder paths with all duplicate subtrees removed. The final result is returned to the caller, completing the implementation. Here, we're tackling the problem of deleting duplicate folders by starting with a simple input. The input is a list of folder paths, and the goal is to create a hierarchical representation of these folders, or a folder tree. We begin with an empty dictionary called root. For the first path, we add a as a child of the root, so root becomes a. Next, for the path, b, we add b as a child of a, resulting in b. This step-by-step process allows us to break down the paths into a nested structure that mirrors the folder hierarchy. Continuing with the input paths, we now process x, which adds x as a sibling of a, updating the folder tree to b, x. Then, we handle x, b, adding b as a child of x, leading to the final tree structure, b, x, b. Once the tree is built, we move to serializing subtrees to identify duplicates. The serialize function recursively generates unique encodings for each subtree, and the subtree_map dictionary tracks these encodings. For this tree, a and x both serialize to b, and the root serializes to a, b, xb. This serialized representation helps us pinpoint duplicate folder structures. After serialization, the subtree_map reveals that the subtree, b, appears multiple times, associated with the b nodes under both e and x. To remove duplicates, we clear these redundant subtrees by deleting the duplicate structures from the tree. The resulting folder tree is simplified to x. Next, we generate the cleaned up result paths by traversing the tree recursively using the collect_paths function. This produces the result, x. This output represents the folder structure after removing duplicates, leaving only the unique top-level paths. For the second example, we deal with a more complex input that includes nested duplicate folders. The paths describe two top-level folders, A and D, each with identical nested structures, B containing C. Building the tree creates a structure where both A and D have the same subtree, B, C. As before, we serialize subtrees to identify duplicates. The innermost folder C serializes to, the B folder serializes to C, and both at and D serialize to B, C. Finally, the root serializes to A, B, C, D, B, C, capturing the entire tree structure. The subtree underscore map now shows that the serialization C appears twice, corresponding to the two C nodes, and B and C also appears twice, corresponding to the identical subtrees under A and D. Since these subtrees are duplicates, we remove them by clearing the B subtrees under both A and D. This simplifies the tree to A, D. Using the collect underscore paths function, we traverse this clean tree to generate the output paths, A, D. This result reflects the unique folder structure, with all duplicate subtrees removed. In the third example, we examine a case with no duplicate folders. The input paths define two top-level folders, A and C, each with distinct subfolders, B under A and D under C. Building the tree results in A, B, C, D. Serialization then generates unique encodings for each subtree. B and D both serialize to, while A serializes to B and C to D. Finally, the root serializes to A, B, C, D. These unique serializations confirm that there are no duplicate subtrees in this example. The subtree underscore map for this example shows distinct entries for the empty subtrees B for A and D for C. As no subtree has more than one occurrence, there's no need to remove anything from the tree. The clean tree remains unchanged as A, B, C, D. Using the collect underscore paths function, we directly generate the result paths A, B, C, C, D. This output mirrors the input, as no duplicates were found, preserving the original folder structure. To analyze the time complexity, we start by breaking the problem into key steps. First, when building the folder tree, we process each folder name across all input paths. Since each folder name is either traversed or inserted into the tree, the cost is proportional to the total number of folder names, which we denote as n. This makes the time complexity of this step O, n. Next, during the serialization of subtrees, the serialize function recursively traverses the tree. For each node, we sort its child folders lexicographically, which takes O, k log k, if there are k children. We then generate serialized strings for all child nodes, requiring recursive traversal of all descendants. Because the total number of nodes is proportional to n, and sorting contributes additional overhead, the serialization step has a worst-case time complexity of O, n asterisk log n. After serialization, we map subtree strings to their corresponding nodes using a dictionary. Both lookup and update operations take O, n, since each node is processed once. Finally, when collecting the result paths, the collect underscore paths function performs a depth-first traversal of the clean tree, visiting each folder name exactly once. This step also takes O, n. Overall, the serialization step dominates the time complexity due to the sorting costs, making it the most expensive operation. Now that we've covered the individual steps, we can conclude that the overall time complexity for the solution is O, n asterisk log n, primarily driven by the serialization process. Shifting our focus to space complexity, the tree structure is stored as a nested dictionary, where each folder name serves as a key, and its value is another dictionary for child folders. Within folder names, the space required for the tree is O, n. During serialization, we use a dictionary to map serialized subtree strings to their nodes. In the worst case, all subtrees are unique, resulting in n entries. The size of each serialized string depends on its subtree size, and the total space required for all serialized strings is O, n. Additionally, the recursive call stack used by the serialize and collect underscore paths functions depends on the tree's height. In the worst case of a completely unbalanced tree, the height is proportional to the number of paths, m, leading to a call stack space of O, m. In a balanced tree, the height is much smaller, around O log m. Thus, the overall space complexity combines these factors. When we combine the major contributors to space usage, the overall space complexity is dominated by the tree structure in serialization data, resulting in O, n. To put this in context, let's compare to a naive approach. A brute force solution might compare every subtree with all others, leading to O, n squared, time complexity, as there are n subtrees and comparing two subtrees depends on their size. In contrast, our optimized approach uses serialization and a dictionary to avoid redundant comparisons. By reducing the problem to sorting and managing serialized strings, we achieve a much more efficient O and log n time complexity. This makes the optimized solution significantly faster, especially for large inputs. To summarize the best, average, and worst case scenarios, in the best case, the tree is balanced, and there are no duplicate subtrees, making serialization and traversal straightforward. The complexity remains O and log n. In the average case, where the tree is moderately balanced and some duplicate subtrees exist, the complexity is still O and log n, as the overall process remains efficient. Even in the worst case, with an unbalanced tree and high sorting costs for child folders, the time complexity remains O and log n, though the constants involved may increase due to the additional sorting overhead. In conclusion, the time complexity of the solution is dominated by serialization and sorting, while the space complexity is governed by the tree structure and serialization data, both of which are O, n. This optimized approach is a significant improvement over the naive O, n squared solution, making it highly effective for handling large and complex inputs. One of the most common mistakes when solving this problem is neglecting to serialize subtree structures before comparing them. Simply attempting to directly compare folder trees is not only computationally expensive but also highly prone to errors. Serialization provides a unique representation of each subtree, making it far easier to identify duplicates efficiently. Another frequent pitfall is failing to include folder names in the serialization process. When folder names are ignored, two entirely different folder structures might incorrectly appear as duplicates because their shapes match. To avoid this, ensure that folder names are always part of the serialized data so that the representation fully captures the uniqueness of each folder. Additionally, edge cases such as empty folders, deeply nested structures, or folders with identical names but different contents are often overlooked. Missing these scenarios can lead to unexpected failures during testing or production. Lastly, inefficient detection methods, such as using nested loops or redundant comparisons, can cause your solution to run in quadratic or worse time complexity. Instead, leverage hash maps or sets to track duplicates efficiently, ensuring your solution can handle larger datasets with ease. Another challenge occurs when solutions fail to delete folders recursively. If nested duplicates are not removed in a bottom-up manner, partial duplicates may remain in the output. To address this, a post-order traversal is essential because it ensures that you process the deepest subtrees first, cleaning up duplicates from the bottom before moving upward. From an interview perspective, this problem highlights the importance of subtree comparison techniques, which often rely on serialization and hashing. Reducing a tree problem to a simpler string comparison task is a critical skill that demonstrates your ability to optimize solutions. Tree problems like this one frequently involve recursive traversal and post-order processing, so practicing these patterns can significantly improve your intuition. Interviewers may also focus on the time and space complexity of your solution, with O, n, time complexity being the ideal benchmark. To achieve this, take advantage of hash maps for efficient duplicate detection. Finally, be ready for follow-up questions about alternative serialization methods, such as using tuples instead of strings. These variations can sometimes improve space efficiency and lead to interesting discussions about trade-offs. If you're looking to deepen your understanding, consider exploring related problems that share similar concepts. For example, in LeetCode 652, Find Duplicate Subtrees, the focus is on detecting subtree duplication, which is closely aligned with this problem. LeetCode 863, All Nodes Distance K in Binary Tree, emphasizes tree traversal and recursion, further sharpening those skills. LeetCode 437, PathSum 3, and LeetCode 226, Invert Binary Tree, are also excellent choices to strengthen your grasp of tree manipulation and recursive problem solving. Beyond problem variations, you might explore alternative approaches for solving this challenge. For instance, custom serialization using tuples instead of strings can slightly optimize space complexity by avoiding string concatenation. However, this approach may be less intuitive to implement and debug. Another option is direct tree comparison, but this method is computationally expensive and unsuitable for large datasets. Finally, top-down traversal could be attempted to detect duplicates earlier in the process, but it's less effective for handling nested duplicates compared to post-order traversal. Each of these methods has its trade-offs, so understanding their strengths and weaknesses can help you refine your problem-solving strategy further. Great work! To summarize, we tackled LeetCode problem number 1948 by using post-order traversal and hashing to identify duplicate folder structures. The approach emphasized efficiency and careful handling of hierarchical data. Remember to apply these concepts in similar problems to strengthen your problem-solving skills. Thank you for watching, and don't forget to like, subscribe, and share this video. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!